Hello, fluid mechanics students. This recorded video is for the class that's being held on Tuesday, the 12th of October. This is class number 15. This is the last of our recorded lectures for the semester. Just to begin with an announcement, your next homework assignment, homework 6, which has to do with both Euler's equation and Bernoulli's equation, needs to be submitted to Blackboard before 11 o'clock on Tuesday, October 19th. Now, in today's lecture video, we're going to look at an additional example of Euler's equation, and I've emailed you a PDF file which has a couple of problem statements. And so we're going to be looking at applying Euler's equation when the acceleration is both horizontal and vertical. And then also looking at what Euler's equation says about a water surface when the liquid is open to the atmosphere. So be sure that you have that handout available and are able to pause the recording to work through the calculations. Additionally, at the end of the video, I spend a few minutes discussing the homework assignment, homework 6. So just kind of tying together the concepts that's introduced with the lecture along to the homework problems themselves. And so be sure that you take a moment to listen to that overview and a couple of hints that I provide. As a reminder, although this lecture is recorded, we are going to still have in-person labs today, Tuesday, the October 12th. And so it will be the first half of the alphabet at 3 o'clock and the second half of the alphabet at 2 o'clock for our lab in room 1228. So I will see you there. Well, this is what we saw in class last Thursday. This is Euler's equation. And this is the version of Euler's equation that you'd find on an equation sheet or reference manual. And what it's saying is that there is a variation in the piezometric head between 2 points. And so the rate of variation of this, excuse me, did I say piezometric head earlier? I meant piezometric pressure. So pressure plus gamma z is piezometric pressure. So there is a change in that having to do with acceleration in the L direction. And so the L here just is talking about a direction. And so what we're saying is that there's a change in the pressure and elevation in the direction of the acceleration, and then how far apart 2 points are that you're applying this at will tell you the magnitude of the difference that's caused by the acceleration. Now, who can remind me what is the interpretation of the minus sign in this formula? Do you recall the significance of that? Anyone?
Is it the one?
Go ahead, Casey.
Oh no, I was just going to say that the one that was, did it have to do with how we chose which one was P2 and P1?
That's a reasonable guess, but no. It's a little bit different from that. It's separate from the 2 versus 1 definitions. Anybody else?
Pressure increases in the opposite.
Spencer?
Pressure increases in the opposite direction of acceleration.
That's exactly right. Yeah. And so what that means, for example, is that if you have a unit of water, whether it's a tank of water or a truckload of gasoline, if it's accelerating one direction, then the pressure is increasing in the opposite direction. So that's exactly right. That's the interpretation of the minus sign there. So assuming linear variation, we would change this rate of change to a delta x, where we're applying this principle in a certain direction. Like if we say there is a component of acceleration in the x direction, then we're going to look at 2 points that are apart from each other and how much distance they have in that plane of the acceleration. And then here we get to trying to differentiate between location 1 and location 2. And then the standard there is that whatever is further to the right in the x direction, having more x, would be location 2. Whatever is further to the left, meaning having less x, would be considered as location 1. So this Euler's equation takes 2 factors into account. It takes the effect of the external acceleration And this, by the way, is local acceleration that causes it causes the pressure change that is quantified by Euler's equation. So this local acceleration, meaning acceleration with respect to time, there is a variation in either the pressure or the water surface, depending on whether the tank is capped and whether the water is able to slosh, whether its elevation is able to change. And so in the x direction, if we're applying Euler's equation horizontally, then whichever is further to the right would be location 2. You can also apply Euler's equation vertically, and then whichever would have the more vertical elevation would be location 2. And remember, the Euler's equation has built in the hydrostatic effect. You do not have to separately account for the hydrostatic effect when you're applying Euler's equation. It simultaneously accounts for the acceleration that is the local acceleration over here on the right side of the equation. But on the left side of the equation, it's accounting for pressure change due to elevation variation. And so the hydrostatic effect is on the left side of the equation. And so what we looked at last time was this example of a truck that was slowing down. And so one of the key takeaways from this previous example was that we have to put the magnitude of the acceleration into A, as well as the direction. And so if it is moving to the right and slowing down, then that would mean that the acceleration that you substitute into A is a minus 3.05. And so directions are really important in Euler's equation in order to get the correct pressure change between 2 points. So what we did was we found the pressure change from T to A, and that was caused exclusively by it slowing down. If it was driving at a constant velocity, or if the truck was stationary, then location A and location T would have the same pressure because they're at the same elevation. But when there's a local acceleration involved, a slowing, then the pressure increases in the opposite direction of acceleration. So since it's slowing down, that means the acceleration is to the left. So the truck is moving forward, but it's moving forward at a slower and slower rate. So that means it's decelerating, or in other words, the acceleration is to the left. And so the pressure increased from T to A, and the acceleration was in the opposite direction. The acceleration was in the direction of from A towards T. And then when we considered the difference between location B and location T, we were able to jump from that point T to location B directly because there's only acceleration happening in one direction in this example. In this example, the acceleration was only in the x. And so Euler's equation automatically took into account the elevation difference between the 2 points, and then it also took into account the distance between them. The 6.1 meters is what we substituted into the delta x, and we were able to find the point of maximum pressure. So that was what we did last time. We had just a single direction of acceleration. Now, you can use Euler's equation to predict what is the pressure gradient inside of a pipe. Now, it's kind of a chicken and the egg conundrum. You sometimes wonder what's causing water to increase its velocity through a pipe. Is it an acceleration that's causing the pressure change, or is it a pressure change that's causing an acceleration? I think it's really kind of a simultaneous thing. But what this illustration is going to show us is that you can find the change in pressure, and when it says a gradient, that means per unit of length. And so if you want the water to be speeding up as it flows through the pipe, meaning that over time the flow rate is increasing, you can use Euler's equation to predict that. All right, and by pressure gradient here, we've defined it as delta P divided by some distance delta L. And so for instance, if A and B are a meter apart, if delta L was 1 meter, then what we want to know is what is the change in pressure between the 2 points. All right, so now let's consider some of the lessons that we already know about this local acceleration. Local acceleration is when the velocity is increasing with respect to time. So we're not talking about convective acceleration. Remember, convective acceleration is the change in velocity with respect to position. And that won't occur in this pipe because it's a constant diameter pipe. And so whatever the velocity of the water is at A, that's going to be the same velocity of the water at B, because the fluid is incompressible and because the diameter of the pipe is constant. And so VA and VB are the same at this instant in time. But because it's accelerating with respect to time, then that means that the velocity 2 minutes from now will be higher than the velocity right now. So I just wanted to start us off by differentiating between the convective acceleration and local acceleration. So this is local acceleration. All right. So if the acceleration is to the right, then that means that the pressure increases in the opposite direction. So there's more pressure at A than there is at B. And conceptually, if you think about just the principles or what's logical and reasonable, that makes sense, right? That if there's more pressure at A, that's going to be forcing the water towards B. That's what's causing the acceleration here, is there's more pressure at A than there is at B. And just like wind, wind blows from locations of high pressure towards locations of low pressure. Or water flows downhill. You know, fluids move from where the energy is high towards where the energy is low. And pressure is a form of energy. And so there's lots of pressure at A, less pressure at B. The water will flow from A to B. So what I'd like to do is I'm going to pause for a moment, and I'm going to ask you to find out what is the pressure gradient. So the way to solve this is you're given the acceleration, you know the acceleration distance, the acceleration direction to the right, meaning positive. It says here that it's water, and so that will define the density of the fluid. Since it's a horizontal pipe, then that means that ZA and ZB are level. And so why don't you see if you can expand out Euler's equation, meaning to this form, and use it to determine what is the pressure gradient. So if they're 1 meter apart, what would be how much pressure, how much additional pressure is there at A compared to B? So what's the rate of pressure change per unit of length? Okay, so we've got this pipe and we want to find out what is the pressure gradient. So let me see if your calculations line up with what I've been doing here. Okay, so we can see A is to the left, B is to the right, and so if we're accelerating it in the x direction, then that means that location B is going to be like what we call 2 when we substitute into this formula, because it's further to the right. And so expanding that out, it's going to be the pressure at B plus gamma ZB. So that's location 2. And then minus the piezometric pressure at location 1. So that means minus PA minus gamma ZA. And so I want to just point out that the minus sign here distributes through to both terms. And so that's a mistake I sometimes see students making, is that they miss the minus sign distributing through. Now ultimately it may not matter in this case because it's a horizontal pipe, and both the gamma ZB and the gamma ZA are going to be canceled out, because ZA and ZB are the same, so there's no difference between them. But it pays to be consistent. It'll come up. Okay, so let's look at some of these substitutions here. We're saying that ZA and ZB are the same because it's a horizontal pipe, and so then that simplifies our expanded Euler's equation. So if we take out the elevation terms, then all that's left is PB minus PA is minus delta x times density times the acceleration in x. Now, remember before what we said is there will be more pressure at A than at B. Like, just logically, you know, based on what we know is going to be happening, the pressure has to be bigger at A to be forcing the water towards the right. And the reason why it's accelerating towards the right is because of the pressure being larger at A. So what does it mean here? If A is bigger than B, then we can expect to have a negative number from this. So PB minus PA is going to be negative. All right. Now, pressure gradient means the change in pressure over some distance. And so if I rearrange that, PB minus PA is the change in pressure. And you can see that we would expect the pressure to be 6,000 pascals per meter. So the pressure is decreasing 6,000 pascals for every meter of length. So in the end, we're just multiplying the density of the fluid by the acceleration. And it's accelerating to the right, so that's why we put in the positive 6. The acceleration will the water will accelerate to the right if the pressure is higher on the left. So any questions about this example where we were looking at a local acceleration inside of a pipe? So the pipe was stationary, but the water was moving. Euler's equation applied here because of a local acceleration. Peter, have you got a question?
Yes. The 2 is always the greater in the Euler's equation.
Yep.
Right?
That's exactly right. Yep. And so here, this was a horizontal pipe, and so B was 2. Let's say, what if we twisted that pipe so that B was up above and A was down below? Then if our acceleration was in the vertical direction, then that would mean whatever is above the other one would be considered 2. And so B would be location 2 in that case. Any other questions? Okay. Now, the spreadsheet, excuse me, not spreadsheet, the file that I emailed you before class is this. And if you're able to print it out, that's great. If not, that's okay. You can just write on a scratch piece of paper. So in the first example we just worked today, it was a stationary pipe and accelerating water. Euler's equation can also apply if the container is accelerating. And so the liquid inside the container isn't moving with respect to the container, but it is still moving with respect to its location on Earth. And so let's take this example of an enclosed tank of mercury. And mercury is always exciting because it has such a high density. Here we're given that the specific gravity is 13.56. So it's accelerated to the right at 15 meters per second. Now we, by our commonly accepted standards, to the right is positive. That's where we're, by definition, we're saying that in the x direction to the right is positive. So it's accelerating at a positive 15 meters per second. But it's also accelerating downward. And so what we have to do when we have acceleration in two directions is you have to take them individually. Now let me emphasize this, because every semester there's a student who tries to combine the accelerations together, and it doesn't work. You can't do it. So it's not like you square both of them, add them together, and take the square root. That's not going to give you the combined acceleration. You have to treat the acceleration separately. And so We know the pressure here at location G. So down in the left corner, we know that the pressure is 485 kilopascals. And so it's accelerating to the right, and it's also accelerating down. So now let's think conceptually before we go any further. So there's location G, location F, and then over here to the right is H. Okay, so if it's accelerating down at 12.5 meters per second, so that's more than G. G is 9.81 meters per second. If it was accelerating down at G, then the pressure at this location and this location would be the same. You know, like that would be weightlessness. No pressure variation. But since it's accelerating down, what that actually means is that the pressure at F is going to be bigger than the pressure at G. This downward acceleration is overcoming the hydrostatic effect. Okay, so we're going to have to find the pressure at location F, and just to set expectations for, you know, when we do crunch the numbers, we should see that the pressure is larger than 485 kilopascals at that location. Now, that's what we'll do first. You'll use the downward acceleration and Euler's equation. I think, oh, did I not paste it in? I thought maybe I would have done that. Let me grab it from over here. Here is Euler's equation in Z and in X. So the first thing you're going to do is you're going to use Euler's equation in the Z direction in order to determine the pressure at F. And then when that's finished, you start to consider the rightward acceleration, and then you use this version of Euler's equation. Let's see if I can move it up. Then you use this version of Euler's equation between G and H. So the two different accelerations are handled separately in this example. Okay, so what I'm going to do is I'll stop for a minute, and you have to figure out, first starting with this one, what is location 2, what is location 1, what is Z2, what is Z1. And it's pretty common to use the lower location as your elevation datum. And so it's going to feel like you're accounting for the elevation twice, because there will be an elevation component to what's going on the left-hand side of the equation with, you know, ZF minus ZG on the left-hand side of the equation. But then also you're accounting for the delta Z on the right side of the equation as well. All right, well, let me not drop too many more clues. I want to pause for a second and see if you can apply Euler's equation in the vertical direction, and then we'll look at that together before you then continue on forward to find out the distance between H and G. So rather than finding an unknown pressure change, we do know the pressure at location H, and we're solving for the unknown distance. All right, so this isn't it, right? There we go, this one. All right, now it's always a good idea to kind of define all of the given information up at the top and maybe do some preliminary calculations where needed. So for instance, we were given the specific gravity of the mercury, and with that we can determine the density of the mercury and the specific weight, both of which we're going to need in our equations today. You'll notice that we're defining the acceleration with the sign for the acceleration being down, because we define up in the Z direction as being positive. And so here this little statement just to set the stage that we expect the pressure at F to be larger than the pressure at G because it's accelerating down faster than gravity. So here's the equation that we're going to do the substitution into. This is the general form. Well, this isn't the general form. This is the expanded form of Euler's equation in the vertical. And now we've done the substitutions for what is location 2 and what is location 1. So we're saying that F is 2 because it has more z. It's higher than location G. And rearranging this to solve for the only unknown here, the pressure at location F. And so moving the gamma z F over to the right-hand side of the equation, the pressure at G over to the right-hand side of the equation, the gamma z G to the right-hand side, and what I said was let's have the vertical datum be that the elevation at location G is 0, and then ZF is 0.87. So now with all of the numerical substitutions there, this is how we can see that the pressure is going to be higher at F than it was at G. So here's the baseline. It's starting at the known location at 485. And by the way, I've said it before and I'm going to just keep hammering this point over and over and over this semester. It's a really good idea to take a few extra seconds and include the units in your calculations. When you're doing the substitutions, don't just write the number. Don't just write 485 because then, is that kilonewtons? Is it newtons? If you write out 485,000 and then make it clear it's newtons per meter squared, you're going to be less prone to combining numbers together that shouldn't be combined if you include the units with the numbers. You'll avoid mistakes. Okay, so now this is saying that the pressure decreases at G because of the elevation, the pressure decreases at location F compared to G. So we're going up through the fluid between the 2 points, and so ordinarily the pressure would be lower because it's higher in elevation, but the external acceleration of 12.5 meters per second more than balances that out. So we're going to be subtracting, so minus the negative acceleration. So there's this minus sign that's built into the equation, and this minus sign that is with the sign of the acceleration itself. So overall, the pressure as you go up through the fluid would be a little bit less because of it being higher, above, but then because it's accelerating downward at more than G, then that more than compensates for it. So then that means that the pressure at F should be 516 kilopascals. Okay, so now we have completed the analysis of acceleration in the vertical. So that was talking about what happens between F and G. Now we ignore what's going on in the vertical, and now we're going to apply the same analysis in the horizontal. So now just look at the acceleration in X is 15 meters per second. So here's our equation, and you're solving for the unknown delta X. Everything else is given. We know the pressure at H, we know the pressure at G, we know the elevation of both of those locations, and so in the second Euler's equation, in the x direction, the only unknown is delta X. So find out how far apart are they. Okay, so I've scrolled down to look at some of the preliminary stuff for our second direction. We're handling the acceleration in X separate from the acceleration vertically. We can't combine them in a single step. So we know the pressure at G and the pressure at H. Here we're defining that H is the one that's further to the right, so that's what makes it 2. G is on the left-hand side when we talk about the x direction, and then the acceleration in X is a positive 15 meters per second. So here is the expanded version of Euler's equation in the x direction. And things are going to get simple because the horizontal plane, ZH and ZG, are the same. So they have the same elevation. So that's going to simplify. And we know that the pressure change between H and G is caused by the distance between them, the density of the fluid, and the acceleration. You know, that's why, if we look at this picture, why would there be a pressure change between G and H? It's because it's accelerating. It's accelerating to the right, so that means that the pressure at H will be less, and that's what we have here, 120. So based on how much the pressure is different, that tells us the delta x. Has anybody solved for delta x yet? Zachary with the win. He's 2 for 2 today. Making baskets. Keep hammering, as Cameron Haynes would say. All right. So we look at the substitutions there. We rearrange for delta x. Okay, so we've got the pressure difference divided by the minus density times the acceleration in x. That's too zoomed in. All right, 1.79 meters. Okay, any questions about this application? In both of the examples that we've looked at today, whether it was the pipe or this tank, the water was constrained in where it was located by either the pipe or the tank. You know, material was surrounding the fluid, and so it couldn't slosh around freely because it was contained in a pipe. But there are situations where the liquid elevation is free to respond to the acceleration. And before we look at the second example, are there any questions about the first one that we did before we move on? All right. Well, feel free to chime in if there are. So the second question is this. We've got a truck carrying a liquid, and it's water. So it's carrying water. And instead of having like a lid on the top, it's just open to the atmosphere. So you can think of this as, you know, it's like the kind of truck that you'd see, maybe a coal truck, or it's carrying scrap metal or something, but it's filled with water. And they know that this truck is never going to accelerate or decelerate more than 8.02 feet per second squared. So how would you know that? Well, maybe it only has brakes that are good enough to slow it down that much. Or based on the acceleration capacity of the engine, maybe it can't accelerate more than that. So what we're saying is that it has a limit on its acceleration or deceleration, and we're going to analyze it at that maximum limit. We're going to say, what if the acceleration is 8.02 feet per second squared? What Euler's equation can do is it can predict the change in elevation as well as predicting the change in pressure. Here is the principle that we're going to be applying when we get to that example. If you have a tank of water that's open to the atmosphere and it's not yet accelerating, then the water will be level, so it's horizontal. But then if it's accelerating to the right, you kind of know that it would slosh up on the side. Some of you who are the civil engineering students in lab last week, do you remember that I filled that reservoir with blue dye? You probably remember the blue dye that was injecting into our viewing tube, right? And I had to fill it up really close to the top so that there would be enough pressure to force it through that small needle diameter. So I had to fill it to within like a millimeter of the top. And so when you have an open container of water and it's really full, like here I've got a cup, if it's only got an inch of water, I can move around and not spill anything. because it's sloshing around, but it's not going outside of the container. But now think if it's all the way full, if it's, you know, it only has maybe like a millimeter down, you have to move really slowly. So why are you moving slowly if it's full? It's because when you accelerate, it affects the liquid elevation. And Euler's equation can be used to describe the elevation of the liquid inside of the tank. And the way that we do that is that we say the acceleration is happening in some L direction. And when it's accelerating and the liquid level raises on the left, it would happen due to an acceleration in the right. So if you're accelerating towards the right, then it would increase in the opposite direction of acceleration. So that's similar to how pressure is affected. So inside the parentheses on the left side of the equation here, it's actually the piezometric pressure that increases in the opposite direction of acceleration. So it's not just the pressure that changes, but it's also the elevation that can change if the tank is open to the atmosphere and able to have the liquid level change, rather than just having like a lid on the tank, and so then the lid is restraining the liquid from moving. If it's open, then the liquid can increase. And what we know is that the angle, you can see here alpha, is determined by the ratio of acceleration in the horizontal direction relative to g. So the ordinary ongoing gravitational acceleration that the liquid experiences here on Earth, if you are accelerating to the right at g, then the angle would be 45 degrees, because the tangent of 45 degrees is 1. And so if a sub x and g are the same, then that would give you an alpha angle of 45 degrees. And so you can predict, based on how big the acceleration is, what the angle is going to be with horizontal. So that is what we're going to apply in this example. So the second example in that handout is we have this truck, and the bed depth is 7 feet tall, and the truck is 18 feet long. And when it accelerates, the liquid is going to slosh to the left. It's going to raise on the left when it's accelerating to the right. And so what we want to know is, if it's accelerating at 8.02 feet, you can calculate alpha with this equation. So you know the angle, and you know that the total liquid depth can be 7 feet on the left when it's accelerating. So the question is, if that total depth is 7 feet, then how much can you fill it before it accelerates in order to not have it spill? So this is a little bit of an indirect problem here, but it starts with determining the angle. And so what I suggest that you do is determine alpha, and think about this length is 18 feet. And so if it's 18 feet in total length, then that means it's 9 feet from the center back to the edge. So now you're going to be able to calculate the angle alpha, and you know that this is 9 feet. So that'll allow you to calculate this distance, and then 7 feet minus that distance is question mark. Okay, let me give you a second here to think it over and calculate, as a starting point, calculate the angle alpha. Okay, so let's take a look first of all at how we are determining that angle. So like I mentioned, if the total distance from front to back is 8 feet, then that means it's going to be 9 feet from the center axis where it rotates about to the front, and also 9 feet from the center to the back. So the angle is going to be 14 degrees for alpha. So let's see. If we have 8.02 divided by 32.2, and then I do the opposite of the tangent on that, 13.99 degrees. Almost exactly 14 degrees. All right, and so that means, we're either going to have both 14 degrees here, and that would, if this base distance is 9, and we know 14 degrees is this, then we can calculate h. Or we can calculate, it's going to be the same distance, this, for our h. How much lower it goes down on the right is the same amount that it raises on the left. So you can see I set up kind of an analysis here that we want to solve for h, how much further it goes down on the right and up on the left. And it's 2.24 feet. That's the deflection when it's accelerating at maximum. So when it's accelerating forward at 8.02 feet, it's going to deflect up to 2.24 feet. Now, if it's accelerating less than that, then the deflection would be less. Delta H is going to be lower if the acceleration is lower. But this is at the extreme case. So if we know that it's going to be rising 2.24 feet on the left, then that means we can't fill it up 7 feet tall, because if it was all the way full, then the liquid would be spilling out when the truck is accelerating. So we have to leave a little bit of head space. Sometimes that's also called freeboard, not to be confused with the Lynyrd Skynyrd song Freebird. Freeboard. So the distance, the liquid depth would be 4.76 feet. And that's just another illustration of a local acceleration. So it is, the water is changing velocity with respect to time. And it's in a container that's forcing it to become accelerated, but since it's open on the top, the liquid level is also changing and responding in addition to the pressure adjusting. Any questions about this example? Well, okay, that is Euler's equation. Homework 6 has several Euler's equation problems that you should be able to solve now. Today's Tuesday, and on Thursday we'll talk about Bernoulli's. And so let me just pull up the homework assignment real quick so that we can take a look at it together. I think I've got it here. All right, so here's the assignment that I just posted on Blackboard. This is a an Euler's equation, problem 1. So it's accelerating to the left and it's accelerating downward. You're given the pressure at A and you want to find the pressure at M. So you're going to have to do the same thing that we did in the example just now. You're going to have to first of all consider the horizontal acceleration. So that means between A and T. You can't find the pressure straight from A to M in a single step. You have to go from A to T and then from T to M, considering the downward acceleration. So you're considering it in 2 different steps. So that's one Euler's problem. Then you've got another Euler's problem in question 2. That's similar to the example that we just looked at with the truck. Example 3, Another one where we have a free surface of water that's accelerating to the right. Oh, it's moving to the right and it's decelerating. So that's what's causing it to raise on the right side, is it's slowing down. So that's another Euler's problem. And then problems 4 and onward are Bernoulli questions. And so you won't be able to solve those until after Thursday's class. But problems 1 through 3 you could solve starting now.